All right, let's dive right in. Today, we're going to explore this hidden language that connects pretty much everything, from your microwave to the music you love, and even to the most distant stars in the sky.
So, let me ask you a question. What could possibly connect the box that heats up your lunch with the booming sound of a rock concert? And then, what do both of those things have to do with the light from a star that's been traveling for millions of years to reach us? It sounds random, right? But there is one single concept that ties them all together.
And the answer is waves. Yep, it's like the universal language for moving energy around. You've got the waves you can feel, like sound, that need something to travel through, like air. But then you've also got waves like light, which can travel through the total emptiness of space. It's all waves.
So how exactly does a wave, wave? It's a funny question, but it turns out there are really only two main ways that energy can move through stuff. Let's take a look. Okay, so what we're looking at here are the two fundamental types of waves. On the left, see how the hand is shaking that string up and down? The wave itself is moving from left to right, but any single piece of the string is just going up and down. Now, look at the image on the right with the piston. The wave is still moving to the right, but this time the little air particles are getting squished together and pulled apart, back and forth along that same direction.
That first one, the string example, that's what we call a transverse wave. The key thing to get here is that the vibration, the up and down motion, is perpendicular, at a 90-degree angle to the direction the wave is actually traveling. Light waves, by the way, are a perfect example of this.
And that second example, the piston pushing the air, that shows us a longitudinal wave. In this case, the particles are jiggling back and forth, parallel to the direction the wave is moving. This is exactly how sound works. It's just a bunch of compressions in the air hitting your eardrum.
Okay, so now we know the two basic ways waves can move. But to really get fluent in their language, we need to learn the vocabulary, the basic parts that make up any wave. So let's dissect one.
First up, we have amplitude. You can just think of this as the wave's height, or its strength. It's how far the wave goes up or down from that center line, its resting position. So for a sound wave, a bigger amplitude means a louder sound. For a light wave, it means brighter light. Simple as that.
Next, we've got wavelength, which uses that Greek letter lambda. This is just what it sounds like, the physical length of one complete wave. You measure it from one peak to the very next peak, or really from any point on the wave to the next spot where it starts repeating itself.
Now let's bring time into the mix. This is the period, with a capital T. It's the amount of time it takes for one full wavelength to go by a specific spot. So if you were watching a boat bobbing in the ocean, the period would be the time between one wave crest hitting the boat and the next one hitting it.
And right alongside period, you have frequency. They're basically two sides of the same coin. Frequency just tells you how many wave cycles pass by a certain point every single second. So if the period is long, the frequency is low. If the period is super short, that means the frequency is high. It's really the beat or the rhythm of the wave. Okay, so we've got our building blocks: amplitude, wavelength, and frequency. Now for the really cool part. Let's see how all of this information gets packed into one single, kind of beautiful equation. We're going to call it the wave's secret code.
Whoa, okay, don't let the math scare you off. Stick with me here. This is called the wave function. But honestly, just think of it like a recipe. It's one powerful formula that tells you everything. It can tell you the exact height of the wave at any position along its path at any moment in time.
Let's just break it down real quick. See that YMO out front? That's just the amplitude we already talked about, the wave's height. Then inside, that K is basically just a shorthand for wavelength. And the OMA, that's omega, is just a shorthand for frequency. The main thing to get is that this one secret code packages everything we've just learned into one neat little expression.
So, we know what a wave is made of, and we even have its secret code. Let's get to the final piece of the puzzle. How does all of this tell us the one thing we really want to know? How fast is the darn thing moving?
Look at this. You can see the wave in two different moments. First, the orange one, and then a split second later, the green one has moved forward. The wave speed, v, is just how fast one spot on that wave, like its very peak, is traveling. You might hear physicists call this a point of constant phase, but don't worry about that. It's just a fancy way of saying we're tracking the same spot as it moves.
And it all comes down to this one beautifully simple idea. The speed of a wave is just its frequency multiplied by its wavelength. And that makes total sense, right? If you have waves passing by you really, really often, that's high frequency. And each one of those waves is super long, that's a big wavelength, then that wave must be moving incredibly fast.
All right, time to see if you've got it. Here we have 3 different waves and 3 different equations. Looking at their amplitude, their height, and their wavelength, can you figure out which equation goes with which wave? Go ahead and pause here and give it a shot.
Now, so far, we've been talking about things that feel pretty normal, sound and light. But this is where things get really, really weird. I want you to read this quote from our source material. These waves are associated with electrons, protons, and other fundamental particles, and even atoms and molecules.
What this is talking about is the wild concept of matter waves. It turns out the final secret in this language of waves isn't about light or sound at all. It's about us. The fundamental particles that make up all matter, the electrons and protons that make up you, they also act like waves. So the final thought I want to leave you with is this. What does it even mean that you, sitting there right now, have a wavelength?